high energy seminar today, and our first speaker today is Chelsea MacLeod. Chelsea is currently a postdoc at Center for Astrophysics, working on quasar variability. She got her PhD in 2012 from University of Washington, and after that she worked at the U.S. Army, U.S. Naval Academy, and the University of Edinburgh. And she joined Center for Astrophysics in April earlier this year. Today she's going to talk to us about a sample of changing loop quasar. Thanks.
Yeah, so I'm going to talk to you today about a sample of highly variable quasars that we think may represent a very interesting population. So, right, in the current picture, a quasar, or AGN, consists of a supermassive black hole surrounded by a disk-like structure from which is accreting mass, which is then surrounded by a large amount of dust, which obscures the line of sight depending on which viewing angle you have. So in a type 1 quasar, you're viewing the central engine at an intermediate angle so that you're not obscured by the dust. And for a type 2 quasar or type 2 AGN, you're looking through the dust. And therefore, you can't see the inner region, such as the broadline region, where you have broad emission lines. The scale of the accretion disk is on the order of micro arc seconds. So it's impossible to resolve with our best telescopes. But we like to understand the structure of the detailed structure of the accretion disk. So we have to resort to other means. Unfortunately, variability is common to all quasars. So we can actually use variability to probe regions close to the supermassive black hole. So nearly all quasars are variable on the 20% level. And it's likely related to the energy production source, the accretion disk. And as you can see in this light curve here for NGC 5548, the variability is stochastic, aperiodic, and it likely contains reprocessed UV emission. And the best evidence for this comes from recent space-based monitoring of NGC 5548 in the UV and across other wavelengths. So here at the bottom is shown a composite quasar spectrum from the Sloan survey. So this is, you can see the power law continuum, which is variable, and the broad emission lines, which are also variable. And the broad emission lines are typically less variable and lagged with respect to the continuum variations, lagged on the light crossing timescale from the accretion disk to the broadline region. And this enables reverberation mapping. So there's also intermediate type AGN, so here's on the top of type 1 where you see clear, a clear broad H beta line. But then there's also this intermediate type AGN where you barely see any broad components, but you still have a narrow line. You may still have a narrow component of the emission line. So remarkably, these two spectra are actually for the same AGN. This is Farrell 9 from 1981 and 1984. And you can see that there's a large change in the broad emission lines, and in particular the Balmer lines. So this is the so-called changing look phenomena. And and usually this large change in the broad emission lines are associated with large changes in the continuum flux as well. So there have been a handful of these changing look AGN reported over the years, but only recently have this population been extended to relatively higher redshifts, so redshifts higher than 0.1. So this paper was the first quasar above redshift of 0.1 that showed this dramatic change in broad emission lines. So this is a Lamassa et al. Paper. It's a serendipitous discovery of a changing look quasar. On the left, you see the light curve history. So it's a stripe 82, so it has a nice detailed light curve. in the early years. And then several years later, you have another spectrum with BOSS, and shown here is the pan-stars data in blue. And on the right, you see the Sloan spectrum in red, and you have H beta there. If you can see, it's broad, and the BOSS spectrum in black, where the broad component of H beta has completely gone away. Here's just a zoom in on the lines. So on the left, you have H beta, and on the right, you have H alpha. And on the top is the early bright state of the quasar, and the bottom is the later lower state. So you can see after 9 years, you basically have diminished all the broad emission line components to these Balmer lines. Actually, there may still be a broad component to H alpha. So for this quasar, actually there turned out to be archival X-ray observations, both in the bright and the faint states. And they find no evidence for a column in either spectras, in either X-ray spectra. So it's consistent with no variable obscuration. So this is exciting because it may be representing a change in accretion rate, for example. So
the X-ray luminosity change from those two observations?
I don't know off the top of my head. I think it was by a larger amount than the optical, but I'm not sure exactly. Okay, so this motivated a systematic search for more changing look quasars in the Sloan and BOSS surveys, where we started with all DR7 quasars, and then chose those that also had a spectrum in BOSS, so a later spectrum. And then based on Sloan and pan-stars photometry, we chose those that showed a magnitude difference of greater than 1 magnitude. And we came out with a sample of roughly 10 changing look quasars. The definition was pretty loose. I mean, basically, we're just looking for spectra where the H beta lines seem to have either appeared or gone away to the noise limit. And there's some other papers that have also reported serendipitous discoveries of changing look quasars. This is a plot of some of the handful of changing look AGN that have been reported. And then the contours show the SDSS quasars, and the blue crosses are the sample from this paper. And you can see we recovered the first Lamassa et al. Object here in this search. So here's just an example. This is the most dramatic example from that paper. Here you have, on the left again, you have the Sloan photometry in black and pan-stars in blue. The BOSS spectra epoch is indicated here. And on the right, you can see the red is the early Sloan spectrum, the black is the later BOSS spectrum. And not only do you see the disappearance of the H beta broad emission line pretty much completely, and most of the broad component of the H alpha line, but also a very large change in the continuum. So the blue continuum essentially goes away. Here's another example that actually went the other way. So instead of turning off, it turned on. And here in red is the archival Catalina data points, but just for just for this plot, we didn't actually use the data in the selection. So here the early spectrum is shown in red, and the later spectrum is shown in black. And you can see the H beta was not really visible in the early spectrum at all. So in this case, it's not really ideal because in the turn-on case, because we're starting with a DR7 quasar catalog, so most of them will have been defined as quasar by the presence of broad emission lines to end up in that catalog. So actually, we're pretty lucky that this one ended up in that catalog. So this, and I'll get to I'll show you a few more examples of changing lit quasars, but now this time they're found through follow-up spectroscopy. So they didn't have a BOSS spectrum, but they did show a very large change in the photometry going from Sloan to Pan stars. So we followed it up with Magellan, or in this case, MMT. And here's a pretty dramatic example. It's a pretty bright quasar, so it's around 20th magnitude now. And the early Sloan spectrum shows clear H beta and H alpha here. And here's the blue, in the blue is the MMT spectrum. And if you kind of ignore these noisy spikes, you can see that, yeah, that there's no evidence of any broad H beta emission there. And this is very noisy in the red part, so it's hard to tell what exactly happened with H alpha. But it's definitely the blue continuum seems to have vanished. Here's two more examples. So here's MMT and a Magellan follow-up. Yeah, here you can see that the later MMT spectrum, you can see it covers magnesium, whereas it didn't in the Sloan spectrum. So it still does have a little bit of broad magnesium left. And this object, it showed a very large magnitude change, so over 2 magnitudes going from Sloan to Pan stars. And it still has a narrow component to H beta, but the broad component has pretty much gone away. And just last one I'll show. So this is actually a quasar from the paper, from the systematic search, because it has a Sloan and Bos spectrum, which showed it to turn on. But then we followed it up with Magellan, and that's shown in blue here. So it went from the really red, noisy Sloan spectrum, where you can't really detect any broad emission there, to the black spectrum, and then back to the blue spectrum. So it seems to have some narrow H beta there, and it's possible it still has some broad H beta there, but it's essentially undetectable. So this one could be interesting in that it's now redimming. Okay, so to summarize the results from our spectroscopic follow-up program, so out of the highly variable, greater than 1 magnitude photometric changes, for the predicted changing look quasar fraction from those is greater than 15%, and this comes from that paper of the systematic search. But the sample size is very small there. So now from our follow-up, we've essentially doubled the sample of changing look quasars, and the fraction of highly variable quasars is about 20%. And if you just focus on the ones that showed a large magnitude change, larger than 1.3 mags instead of 1 mag, then the fraction goes up to about 30%. And out of the new changing look quasars, about 90% are turn off and 10% are turn on. But again, this is probably biased by the selection of quasars in the quasar catalogs. And finally, these changes occur over rest frame timescales of years, actually some of them are maybe as short as 1 or 2 years, but most of them are over several years in the rest frame. So how can we interpret these changes to study accretion physics? Well, first let's talk about the timescales that you expect to see in AGN. So for an accretion disk, the viscous timescale is the timescale it takes for matter to drift inward radially in the disk. And in for the optical emitting region, it's very long. It's about 10,000 years or so. And in the UV, it's much shorter because it's very strongly dependent on the radius. And so it can be as short as days in the UV. So in the optical, it's very long, but if you can make this timescale very much shorter if you have instabilities in the disk. So now there's the dynamical timescale, which is the shortest timescale you'd expect to see any physical changes. And this kind of encompasses the free fall, sound crossing, and orbital times. And this is about on roughly days for the accretion disk and roughly years for the broadline region. And then finally, you have thermal timescale for thermal instabilities. So at this time that takes for energy to dissipate within the disk, or essentially the response time scale to a spike of energy input. And this is about days to years for the accretion disk. Okay, so what are the observations telling us? How do we interpret them with these timescales? So, well, maybe one idea is you can explain the short, several year timescales that we're seeing in these cumulative quasars if actually what we're seeing is a lot of reprocessed light from the inner regions of the disk where the viscous timescale is much shorter. Another possibility is that we're seeing a global temperature change that happens on the thermal timescale. For example, as this is claimed for Markarian 1018, which is a changing like AGN that has just turned back off after 30 years. Or it could be something other than an accretion rate change. So, for example, variable obscuration, although that seems unlikely given that some of these objects have archival X-ray spectra which show no evidence for changing obscuration. Also, you can't really explain the optical spectral changes using just simple dust reddening. So that's unlikely, but still is a possibility. They could be tidal disruption events. For example, this paper claims to have a good TDE model for one of the known changing quasars. But this is unlikely to describe all the events because some of them have long sustained bright states, which would be hard to explain as a TDE flare. Or it could be the variability could be jet related. This is also unlikely since they're all radio quiet. Or you could have a mixed bag of these. Maybe you don't have just accretion rate changes, but also some quasars just have also a variable obscuration. So for the future, we would like to test the obscuration scenario. So in one way we're gonna do this is to obtain follow-up X-ray observations for changing look quasars, so that have been previously observed in the X-rays in the opposite state. So for example, here's the changing look quasar candidate. We still need to observe it in the optical to get a spectrum to see if it's actually changing its appearance in the broad Balmer lines. But this one would be interesting if it were a changing look quasar because it has past XMM observations in the bright state, and then we could go and get a follow-up Chandra observation in the dim state and compare the two. So we want to do this for a larger sample of quasars to see if all of them are more consistent with an accretion rate change rather than obscuration. And so we were awarded a TRO program, which we're working to follow through with to do this. And also, this provides a really good opportunity for connecting to X-ray binaries because for those, you see these changes occurring on much shorter timescales. So you can measure the X-ray power law continuum slope gamma and find that it actually trends with the accretion rate. It depends on the accretion rate or the Eddington ratio for a given X-ray binary. And this kind of study hasn't really been done for AGN yet, although you can do it as an sort of ensemble and find this trend in samples of AGN. But we'd like to do this for a given AGN. Also, part of the problem is that we don't really understand quasar spectroscopic variability on long timescales in general, just simply due to the lack of data. So this will hopefully change with increasing samples of repeat quasar spectroscopy. And this is one of the goals of the time domain spectroscopic survey of Sloan 4. So this is an EBOS subprogram where we're obtaining optical spectra for all variable sources selected based on variability. And not all variable sources, but to our allowed limit. And this also includes a program for repeat spectroscopy. There's a region of the sky where we'll obtain another epoch of spectroscopy for 15,000 quasars And this plot right here is showing the distribution of rest frame times spanned between the repeat spectra for this quasar sample versus their luminosity. And you can see that this plane is this is after we've observed these 15,000 quasars. This plane is starting to get filled in so that we can study how quasars vary spectroscopically at any given timescale at any given luminosity. And this spans timescales long enough to sample a few dynamical timescales of the broadline region. So we can see if that is interesting at all. And I guess that's it. There's also a subprogram to follow up hypervariable quasars in particular, which is very relevant to this idea of finding more changing look quasars. Okay, and I will end there. Any questions? Uh-huh.
Came back depending on the direction of the node.
Uh-huh.
And yet you stated there was no evidence for obscuration. Could you interpret that in terms of obscuration?
The disappearance of the blue continuum. It can be interpreted in a scenario where you have variable obscuration if something's moving in front of the accretion disk and also blocking out. So you can either have something blocking the broadline region from the observer, or you can have something blocking the accretion disk from the broadline so it can't be photoionized anymore. So you could have some complicated scenario that might cause both the dimming of the blue continuum and the broad emission lines. But also an accretion rate change can explain those too, although, as I explained, that's also possibly complicated to explain. The timescales for the variable obscuration don't really match up either. So it would just, for like a dust cloud to pass and cover the entire broadline region and continue to block the flux, it would take, the very shortest timescale you would expect for that is like 20 years. And these are happening on much shorter than that. So it's unlikely. But.
So you
Yeah.
said that none of the changing look quasars so far are radio loud?
Right. There's one that is a very weak changing look quasar. It's not a very dramatic change, and it had a radio detection. But
But was there bias against radio loud quasars because the variability can be caused by the jet component? In the original selection.
In the original selection, a lot of the blazars and radio loud quasars will have shown up in the variability selection. And in the systematic searches that we did, we didn't select against them at all. We still included them in the search when we were looking through the spectra. So, there were a couple cases where they were clearly blazars and they were just actually, we ignored those, but that was only a few cases.
What's the highest redshift so far? About 1, did you say, in your slides?
So it's at 0.67. Yeah, and that's mostly because we chose to look at the H beta line. So if you're higher redshifts than that, then you won't have the H beta line in the spectrum anymore.
Any other questions for Chelsea? If not, we thank Chelsea. Our next speaker is Michael McCollough. Michael is a archive astrophysicist and he got his bachelor and master's degree from
Okay. Many of you probably have heard me tell you about the little friend, but this is going to be about SIG-X3 and the little friend. These are my various collaborators, Leah Corrales, Mike Dunham, Randall Smith, and Lynn Valencic, who on this work. This work will incorporate some of a paper that I did in 2013, but it'll also contain the new results that just came out this last Thursday in AppJ Letters about some of the follow-up for the little friend. Let's see. Okay, just a little bit about SIG-X3, discovered in 1966. It lies right in the galactic plane in the Cygnus X region. The distance has typically been taken to be 9 kiloparsecs. Sort of remember that number because I'm going to come back to that and actually say a lot more about it. But it has a large uncertainty. It also has a 4.8-hour orbital modulation. The mass donating star is a Wolf-Rayet, and either with a black hole or neutron star. It's not completely clear. Personally, I would lean toward the black hole, but that's still to be determined. And very likely formed from a Wolf-Rayet binary to get this sort of system. It's also a progenitor of the binary that will eventually become a compact binary, which will lead to a gravitational wave source in the future. So it has some interest there. It also has very strong stellar winds. This is a beautiful picture of Jeremy Drake's from the Cygnus OB2 Legacy project. So you see the Cygnus OB2, but here down in the corner is SIG-X3 blasting away. And SIG-X3 is much further away. Also, just a few things on Cygnus X3. One of the reasons it's interesting, has a very complex spectrum, undergoes low to high state changes. There's correlations between the radio X-ray, hard X-ray, and they basically relate to activity. Very bright all the time, 10 to the 37th, 10 to the 38th ergs per second. Even when it does the high-low change, there's actually a pivoting in the spectrum, so that the hard actually, if you see in the X-ray like Chandra sees, you see about a factor of 6 to 8 change when these state changes. If you were to actually include the hard X-ray, it'd only be about a factor of 2 to 3. So there's a pivoting of the spectra where it's putting it out. It also produces very large flares, 20 Janskys during major flares, and relativistic jets. So SIG-X3 is actually a microquasar, and in truth, it's more likely a microblazar. This is actually from a 1997 observation of the jet, and it's, as in this case you can see, it's essentially one-sided in these observations. You can often see the counterjet, but it's much weaker and consistent with these sort of velocities. This is these are observations from last month. SIG-X3 had been in a 5-year hiatus for major flare activity. And last month it decided to change all of that. You can kind of see it here, but it actually double pumped. It had 2 major flares. Both of them got up to around 18 Janskys, down around 1 gigahertz. This is a talk for later. We're going to talk about actually the little friend, which will actually tell us stuff about SIG-X3. In 2000 observation, there was a feature that's within 16 arc seconds here. Initially by Heindel et al. And their analysis pointed to being a stellar wind observation, interaction, excuse me. In 2006, we had a longer observation of SIG-X3, and it was during a quench state. So SIG-X3 was very bright in the Chandra band, and it gave us much better insight. First of all, this feature is extended, 3.6 by 5.5 arc seconds, so you can resolve it in Chandra. And it varies in phase and intensity with SIG-X3. SIG-X3 gets bright, it gets bright. And if it were at the same distance as SIG-X3, that distance would be about 2.5, 3 light years. So this is almost immediately responds to whatever that, and it also varies in phase. There's a phase shift of about 0.56. And in fact, if you phase cut the data, phase fold and cut the data, now you see it, now you don't. So in this, and just to sort of reiterate that, if I can, when you have lots of photons with SIG-X3, you can make a movie, and you can actually see the little friend fade away as SIG-X3 gets bright. And then and what this is it's a 50 kilosecond observation. I've taken 10 kiloseconds, about 0.2 in phase, and then I slide this in phase throughout the entire data set to create the movie. And so that you can actually see that they're varying with one another. Now, the solution to this, you look at and you try to understand what's going on, but the most natural thing is this is a scattering phenomenon. is that basically it's small angle X-ray scattering giving rise to this. The little friend is much smaller in terms of the total. It's not overlapping sig X3, so that's why you see it as this discrete instead of a ring. And it's actually acting as a mirror. This also can explain the phase difference. In fact, that phase difference becomes important because that phase difference allows you to actually say something about where the little friend is relative to sig X3. And it also explains why there's the correlation, why there's only 10 to the minus 3, why the lower flux amount from the little friend, because it's a scattering phenomenon. It's only intercepting a small fraction. And so this will explain why you see what you're seeing. Now, some stuff I'm not showing, as I've done spectral fits to the little friend, I can actually estimate what the column density through the little friend from the scattering is. And it's on the order of 5 times 10 to the 22nd. This distance of 7 kiloparsecs comes from the scattering relationship, which I'll say a little bit more a little bit later. But it implies the size is on the order of 1/10 to 2/10 of a parsec in size for the little friend. And in fact, if you take that path and use the column density, you can get a density for the little friend. It's 10 to the 5th particles per cubic centimeter, which makes the little friend a molecular cloud. It's a tiny molecular cloud. Assuming it's roughly spherical in size, you can say that the mass of the little friend is between 2 to 18 solar masses. So it turns out that actually using all that information tells you the little friend is actually a well-known class of objects. It's what's called a Bok globule, except that most people, when you see Bok globules, tend to see this in the optical, these little dark clouds. Their temperatures are on the order of 10 to 20 K, so they're cold. So you're actually getting X-rays from this source is actually, because it's scattering from a very cold source. And this is also where you also see evidence, usually many times, for star formation. So we can actually are seeing basically an X-ray detection of a Bok globule. So, and you also see that it will also, you often get other little structure associated with it. Now, to kind of get more at looking at it, to understand the structure, what we did is created basically a PSF from the right half. Most of the features are on the left half of the image I showed you. And so we actually use ZH tools to create a PSF and then subtracted and normalized the image by it. Now what you've also done is mask out the readout streak, but you see the little friend, but you also see it even has a little what appears to be tail or structure like the other Bok globules, similar to what you see there. You also notice this is actually a node boundary here in terms of being dithered. And so you actually see instrumental effects as well. We actually kind of believe this feature here actually may be real. That's an area of still active research as to how real that is. But you do indeed see the little friend, and it appears similar in structure to what you see in the Bok globule. And again, just because I have lots of photons, we can make a movie just with sig X3 move and just the little friend. And you can also get some sense of actually, as it goes on, how the light propagates outwards. So there's actually even a delay across the little friend that you can measure of about an hour. And so you can actually come and see it go as a function of phase. Now, we would like to confirm this. This is actually part of what we did in terms of proposing. And so what we did is went to our friends over at the SMA, across the street, and said, hey, how about let's see if we can find this. And believe it or not, I managed to convince someone to do that. And so we put in an SMA proposal. We were granted actually one track. The reason we got 2 tracks is we actually had bad weather. And what bad weather in SMA means high moisture content one night. It was usable data, but didn't give us a lot. But still, we got 2 tracks at around 230 gigahertz. And so we can simultaneously get 12CO, 13CO, and C18O in the J to 2-1 line. So basically molecular CO, and we can also get continuum information. So what did we find? There's a counterpart. So we've actually found the molecular counterpart. For that, we actually see even the little knot as well as the little friend. This here we'll come back to. Because that actually says something else, something a little not quite expected. But anyway, and the contours here are 2, 3, and 4 sigma levels. And so it's well detected. We also use 13CO. It's a rarer isotope, and so we think and believe it will be more centrally concentrated and will better fall where the structure of the globule will be. And sure enough, we do, and we get it occurs at velocity minus 47.5, and in fact, we see CO in the minus 44 to minus 49, which is putting you out really right around the Perseus arm. Okay, and so we will basically look at the data. What we see is if we look at the continuum, we don't see it. Now, what you expect from the continuum is actually the dust itself. If the dust is at 10 to 20 Kelvin and it's being heated, you would expect some emission, but we don't detect any. Now, what that means is that we're on the low end of the mass. We just don't have that much dust, and so that the little friend is actually at the low end of the mass that I gave you. And so our 3 sigma limit puts at about 4.2 solar masses, gas plus dust, and so we're right at the low end inferred from the X-ray. Still very consistent. But the nice thing is I noticed about the minus 47.5, well, we can do something with that. In the fact that if we assume that the velocities of the shift are mostly due to galactic rotation, that information can be used to actually deduce where the little friend is located. And in fact, you have to be a little bit careful when you're going out around the Perseus arm because there is some very higher velocities than normally what you might expect. So what we used was a tool that Mark Reed had, which is a Bayesian parallax-based distance estimator. And so it goes in with several priors, such as the spiral arm, the kinematic distance, and galactic latitude. And so what you get is a probability density curve, which you have 2 peaks. The lighter 2 gray peaks here are just going at the minus 44 and minus 49, the range at which we see CO. And so from the 2 peaks, we get the most probable peak at the 40 is at 6.08 plus or minus 0.64 kiloparsecs with a 62% probability. And then a secondary peak at 7.85 plus or minus 0.6 kiloparsecs with a 38% probability. And so what we have taken is we take this one as being that this is the most probable distance. But what it also tells us, this also confirms this is not only an X-ray detection of a Bok globule, but it's the most distant one seen to date. Prior to this, most Bok globules are seen at a distance of around 2 kiloparsecs is the furthest away. We're seeing one at 6 kiloparsecs. And so it's also, what's nice about this sits this right down in the Perseus arm, right where the local branch comes into the Perseus arm, which should be a rich star-forming region. So it all is a consistent picture of the little friend, where it should be found. And so this is all very consistent. Now, I've just said, though, we have an X-ray information from Chandra that relates the little friend to Chandra, so we can say something about how far away SIG-X3 is. Using the X-ray time delay for the scattering, these are basically the time delay that we see. This is the distance to the little friend, which is dx. This is the distance away. We solve for the relative x, which is 8.5. This gives us a distance of 7.41 plus or minus 1.13 kiloparsecs. Okay, so I've just put the distance to SIG-X3 went from 7 to 13 to 7.4 plus or minus a kiloparsec. So it's about 15% error bars. So fairly a good improvement. There is a estimate by Ling, which is about 7.2, which is in relative agreement to this. Okay, and so this is probably one of the best measurements. And so we can actually really say much more in terms of SIG-X3 in terms of where the energy output, budget, things like that. So we have now a really much better idea of where SIG-X3 is. Now there's a question, and unfortunately on this they don't show up real well on this one, but I'll take care of that in the next slide. In the original 2013 paper, we looked at how are these related to one another. And I ended up putting out 3 scenarios. One is just random alignment. This new distance estimate really doesn't change any of that. It's because it's sitting right in the plane. So it could easily just be a random chance it just happens to be sitting there. There's also been a scenario where a microquasar jet may be inflating, and this may be a point at where it's interaction, where the working head of a microquasar jet is existing, because SIG-X3 is aimed at us, and it may be where the jet is hitting. And with the 1 kiloparsec roughly separating the SIGX3 and the little friend, that is not unreasonable. There's been a case of one where the distance was about 300 parsecs. So this is a little bit long, but it's not completely unreasonable. But the one where we proposed a super bubble giant shell in which a association drives a huge shell, that's a lot less likely because we're now sticking on here, SIGX3 is sitting out in the inner arm region. Now, this new sort of location gave us to speculate, well, if that's the case, there may be another way of getting there and another way of explaining it. And the way to do this is you would expect a Wolf-Rayet binary to really be formed in a star-forming region, like where we find the little friend. So one, and this is just a guess, is CX3, if it formed in that same star-forming region and experienced a natal kick from when the supernova formed the X-ray binary. And if we just make some assumptions of 1 kiloparsec distance and then an assumption of 1 to 5 megayears for the lifetime of a Wolf-Rayet as being when this event could have occurred, we arrive at a natal kick of somewhere between 190 to 980 kilometers a second. Now, what do observations say? Well, there's some work by Hansen et al. In 2000 where they actually constrain the magnitude of the systematic radial velocity to be less than 200 kilometers a second. This is from infrared spectra. And so this basically fits at least at the lower limit. So this would put this. Now, there's also another paper by Fritz Perels in 2000 where he looked at Chandra spectra, and what he found is that all of the lines were shifted by about 800 kilometers a second. Okay, so this puts it more closer to the top. And this is an area which I'll get to right at the end of the talk, where we're going to try and actually look at this actually in a little bit more detail. As I said, this is a little bit better. I should have also put on, you are here, okay, in this. So here's the little friend. Here's where Cygnus X3 would be relative on a scale. Now, something else unexpected. I noticed that little feature. And, you start looking at the data and what you end up discovering, well, SIGX3 is not the only guy that has jets out there. The little friend has its own set of jets or outflows coming out of it in CO. And what that tells you is not only is the little friend a Bach globule, a nursery for star formation, stars have actually begun to form. You actually have a protostar that's actually already generating outflows from it. These are the red and blue shifted. Okay, and these have been observed in other Bach globules, other molecular clouds have been seen to have these outflows, so it's not a complete surprise. What I like about this picture is what I refer to it as the stellar cycle of life. SIGX3 here represents stellar death. In fact, it's going to even undergo a bigger death shortly because it's a Wolf-Rayet in a compact system, so it's going to end sooner than later. You have the little friend in the X-ray, which is a stellar nursery, and then you have the outflows indicating somewhere in here is a protostar that is turned on and generating an outflow. Now, in terms of just a little bit of, in terms of information physics of the little outflows, these are blue shift and red shift components. These give the size and the radial. These are very typical for what you find on these outflows. In particular, and these low velocities have been observed in several mass-forming regions. We've estimated that the resulting outflow is around 7/100ths of a solar mass. This puts that the outflow is not unusual. It sits at the top end of what you expect for mass flows out of these type of systems, but it's all consistent with that. So these are the results that were put out, and just have recently come out this last Thursday in an AppJ letter. Now, what I will go to here is just basically in terms of a statement, some of where are we going now. And this actually involves some people in the room. This is the SIGOB2. If you notice, it has this beautiful scattering halo. And so there's actually some work to do that. One of the things I didn't tell you, there's other CO, but it's actually much nearer because we are actually looking through the SIGOB2 association. And the SIGOB2 association, if you look at the CO, you can actually see that it has two walls of CO either side of it. And so that this scattering halo will tell us more in terms of both in terms of information about SIG-X3, but also even in terms of the environment. I am actually been doing some preliminary stuff with Margarita concerning getting better imaging. That X-ray image I showed you is half arc-second pixels. We can do better than that, and we may get actually more detail, even potentially try to find the protostar, although that I think will be difficult. If it would be probably one of the most distant protostars that we're seeing. Also, too, we have proposed and have accepted for this 2-cycle to actually follow up with the SMA, one to do it at higher resolution. Our resolution is about 3 arcsecond in the CO, and we would get arcsecond sort of resolution. Also to do a subcompact array to actually try to make sure we're getting and measuring all of the CO. You worry with interferometer that you may be missing some of it. A proposal that Saku and myself have put in for Gemini North is we want to follow up and do some Doppler tomography on SIG-X3, but this will also, from the infrared, we'll also try to address this, to do a better job of addressing this. That way we can actually say more in terms of the natal kick. And as I noted about the Chandra observations, and what Fritz did is he was using an early set in a lower state, not one of the low states, and the lines themselves was a shorter observation, and the lines themselves he just fit with simple Gaussians. We actually know now, looking at SIG-X3, especially from the really bright state, it has almost all those lines have P Cygni profiles. So we need to go and refit those lines, and I suspect that 800 is going to drop back down and be pushed more toward the middle. And then in terms of my final slide, just to say what the future, and this is in terms of people who have been involved with X-ray surveyor. With Chandra-like resolution and you increase an order of magnitude throughput in a large flat field, you can really actually start extending this reach to these sort of halos, and actually some of what I've shown you here for SIG-X3, you start dropping down to a larger range of sources. So you can study a much more range of dust halos, which will give you information, again, about some of these sources in terms of distances, potentially, if you can find scattering features. This becomes a probe in terms of the galactic structure through the dust, better understanding of dust and grain composition, and then also even probing, in particular with time variability X-ray sources, probing star-forming regions. As young stars flare or whatever, if you can get these dust halos, you gain information. Thank you.
So Mike, I've got a question or two and then a comment. The questions are, what's been done in the infrared already? Has there been any HST, J and H?
There's been Nick Moss observations. For SIG-X3, you see SIG-X3. It's there, but the little friend you don't see. There has been the MIPS 25 micron. If you look at it, you see SIG-X3, you see this sort of extended feature around SIG-X3, and you see something that could be the little friend. It's an enhanced emission, but the combination of the resolution and all of that, you can make speculations about it. But there's nothing, at least I have seen, high resolution infrared out at the mid to longer wavelengths.
Then the comments are the X-ray heating must make appreciable complications, let's put it that way, for all that dust. In fact, I would think it would sublimate it. So, but you're seeing scattering primarily from the dust, or can you explain it from the gas?
Right now, it's really primarily from the dust is our modeling so far.
Have you done any calculations of what happens to the dust?
No, and that's something we've got to do. We're still about a kiloparsec away. So, but we still, I agree with you, and that actually gets to interesting questions too. Is we do see it in CO, but also there may be interesting stuff in terms of chemistry and other things that are going on.
And the other quick comment is that velocity of up to 800 kilometers a second would be totally inconsistent with any black hole kick.
Yes.
I mean, by factors of 3 or 4 probably.
Well,
But even for the neutron stars, it's I think not going to work because we see isolated pulsars, but here you've got a kick binary.
Mm-hmm.
And that's a massive star. What's the estimated mass of the Wolf-Rayet star?
The Wolf-Rayet star, well, that can vary, but the numbers I've typically seen or typically been estimated is something like 20 solar masses or so.
That's what I would expect.
Yeah.
I think that's a very hard thing to.
Well, like I say, the top range just comes from assuming 1 megasecond versus 5. And so that's why, like I say, I couldn't really limit it much more. But the 800, like I say, I think those numbers will come down. That's actually something I'm in the process of doing, is reanalyze. I'm doing an analysis in terms of actually fitting the lines and correctly fitting them with P Cygni profiles versus just a simple Gaussian. And that's what Fritz actually did, was a simple Gaussian. So I'm fully expecting those 800s will drop a good bit. So I'm expecting, at least from a measurement point of view, that will come down.